Good, so we've done this experiment on finding the charge on an electron and you've got an answer. Hopefully you've got quite a good answer, but the question really that we do a lot of this year is, how do we know how good that answer is? Okay, we can look at the uncertainty in our answer. So if you've told me an answer, are you confident that that answer is exactly correct? Is it correct to 2 decimal places, 3 decimal places? Might you be 50% out? Might you be 75% out? Might you only be 1% out? Okay, these are the conversations that we need to be able to have. This is what's called uncertainty. So we need to be clear what we mean by that. We need to know the causes of uncertainty, and most crucially, we need to be able to estimate the uncertainty in a value we've got. So once you give me an answer and I say to you, how close do you think the answer is to the correct answer, you need to be able to actually estimate how far out you might possibly be. Okay, so what is uncertainty? Well, no reading is 100% correct. Right, there's always likely to be a difference between the value you've written down and the actual value. So what have we got? Well, we've got random errors. Okay, so this is a key term here, random error. This is when you think you're going to do exactly the same thing over and over again, but you don't get the same result every time. So if I said to you, for example, hold the ball 1 metre off the ground, drop it and time how long it takes to hit the ground, you're not going to get the same answer every time for lots of reasons. That might be to do with your reaction timing in that example. Okay, there's various other things that might cause random error. Okay, but these are just doing the same reading over and over again and not getting the same answer every time, even though you think you've done the same things. The second kind of error is called a systematic error. This is an error which is built into the experiment. So you might do repeats and you might get the same answer every single time, but they could all be the wrong answer. Okay, so sometimes people are very confident because they've got the same answer when they've done an experiment 3 times or 5 times, but in fact all of those answers are wrong. Okay, and then the third possible reason why your result isn't 100% correct is even if you've eliminated all the random errors and all systematic errors, there's still a precision of the instrument which limits you. So things can't measure, your balance for example can't measure exactly what the mass is. It can only measure the mass to the nearest 100th of a gram in the experiment that you did. So even if you think there's no errors from these things, no uncertainty in your answer, the precision of the instrument will always limit how close you can actually get to the correct answer. So what we're going to do is to try to apply these ideas to the experiment you did. So think about the uncertainties you've got. Well, the current will probably change in this experiment. So this is a random error. We'd like it to stay the same throughout the experiment, okay, but it probably won't. And you notice it's changing because not only is it changing a little bit, but it's changing more than the instrument precision. So, for example, you might do this experiment and start at 0.55 amps and end up at 0.51 amps. So what you should really write the current down is do a simple kind of average in your head. We could record the current every few seconds and work out some kind of more mathematical average, but good enough for us probably on this is to just say that's 0.53 plus or minus 0.02 amps. So the biggest current was 0.55, that's 0.53 plus 0.02, the smallest one was 0.51, so that's 0.53 minus 0.02. So I can say the average current is 0.53, but it's plus or minus 0.02. So this is a way of writing the uncertainty in a reading. Okay, this is crucial that you understand this kind of method of how we actually record the uncertainty in one value. Okay, there's timing error. This is a kind of error which is another sort of random error. So 10 people might do that experiment and they might all say they've done it for the same time, for 10 minutes in this case, 600 seconds. But, you know, some people might be the person breaks a circuit and says, okay, stop, and the other person might say, okay, stop, and then the person breaks a circuit. So we might end up 5 seconds out. That might seem like quite a big uncertainty to you, but you'll see in a bit that's probably not something we should be overly stressed about. So the time in this experiment is 600 plus or minus 5 seconds. And then we look at the mass. Well, the mass balance is only plus or minus 0.01 grams. This is instrument precision. So it's plus or minus 0.01. Some people think, well, it must be plus or minus 0.005 because if I get an answer like 1.5, it can't be as much as 1.51 because then it would say 1.51. But what you have to remember is that when you tear the balance in the first place, you don't know it's exactly 0.00. It might say minus 0.004 and go up to 1.54, and then overall that would have made the mass 1.5 grams. So here's some more data that you might have got. So you've got 1.5 grams to 1.4 grams. Now 0.01 grams out of 1.5 might not look too bad, but what you've got to remember is we're not interested in how much this is. What we're interested in is the difference. So the difference of these two masses is only 0.1 grams. This one might be 0.01 out, sorry. This one might be 0.01 out. So the total uncertainty is 0.02. Okay, it could have gone from 1.51 down to 1.39 and be 0.12 grams, but it might only have gone from 1.49 to 1.41, and the difference might be only 0.08. Okay, so our uncertainty is 0.1 plus or minus 0.02 grams. So that's all very well. We've got our uncertainty in the different data that we've got. So we've got our current was 0.53 plus or minus 0.02, the time was 600 plus or minus 5, the mass was 0.1 plus or minus 0.02 grams. So the next step is to find the percentage uncertainties. If I said to you, well, which of those is the biggest problem? It might be tempting to say, well, 5 is the biggest uncertainty, so surely 5 is the biggest problem. But it doesn't matter how big this number is. What matters is how big is this number compared with this number. So what we do is we turn these into a percentage. So 0.53 plus or minus 0.02, we do 0.02 divided by 0.53 times 100. You get 4%. Now some of you might be thinking that's not exactly 4%, but we don't know how far out we are anyway. So if that comes to 3.9%, we just round it to 4. 1 or 2 significant figures is plenty for uncertainties. Okay, the 5 seconds out of 600 seconds is just less than 1%, but the 0.02 out of 0.10 is 20%. So when you look at these numbers, it's hopefully is fairly obvious that the mass is the thing we should be worrying about, whereas if we're a few seconds out in the timing, we don't really worry too much. Okay, there's nothing complicated in this experiment. We've just multiplied these two numbers together and done our stuff with Avogadro's number and stuff, so nothing squared. We'll come back to that later. So in this experiment, it's fairly straightforward. All you do is add the percentages together. So 4%, 1% and 20% makes 25% altogether. If you do the maths on this, the answer came to 1.68 times 10 to the minus 19. Work out 25% of that number. That comes to 0.4. Again, we've just rounded to one significant figure for this. So 0.4 times 10 to the minus 19. So the way we would write this answer is 1.68 plus or minus 0.4, but there's not really too much point in us worrying about this 8 if we don't know if this number's it could be a 3, a 4, a 5, a 6, a 7, an 8. So why are we worrying about this number? So I'd round this to 2 significant figures and make this 1.7 plus or minus 0.4 times 10 to the minus 19 coulombs. So now we'd not only have an answer for the charge on the electron, but we'd also know the answer was somewhere between 1.3 and 2.1. So if you've all done that in a class, anyone who's got outside that range, if one person says it's 1.7 plus or minus 0.4 and somebody else says no, it's 2.5 plus or minus 0.2, all right, they can't both be right. One of those has got the uncertainties wrong. They're not as precise as they think they are. Okay, but that's how we write the final answer. Okay, here's our answer. Here's the uncertainty in our answer. Anything you look up in a sophisticated enough textbook will tell you all these masses and charges and things, plus or minus the uncertainty. We don't know any number exactly. Okay, we just know them within a certain range. The better your experiment is, the smaller your uncertainty becomes. Okay, that has another knock-on effect for this, which is that we can see which is the biggest problem. So clearly the biggest problem was the mass loss of the electrode. It was a 20% error. So if you wanted to get a more precise answer, an answer with a smaller uncertainty, okay, then what you do is that you would probably run the experiment for longer. You would get a bigger mass loss, and therefore you would get a smaller percentage uncertainty. You might get a bigger change in the current during that time, which might increase the uncertainty in the current, okay, but the uncertainty in the current was only 4%, so if this error goes down to, say, 10% and the uncertainty in the current goes up to 7 or 8%, we've still got a better answer overall.